Okay, so let's move on to the question. In one form of Tesla coil is some kind of setup that you usually see in a museum. It involves people create like lightning around the area, then they use this Tesla coil, but not important. Okay, so in one form of Tesla coil, you have a long solenoid with length of L and a cross-sectional area of A. Okay, this long solenoid here has a length of L, cross-sectional area of A, and is closely wounded with N1 turns of wire. So you can see that this solenoid here has N1 turns of wire. Now you have another coil with N2 turns surrounded at its center. So N2 turns here is another coil, but it is wounded coaxially with the solenoid. When I say coaxially, means by they share the same axis, they share the same center. That's the meaning of coaxially. Okay, so you have another coil here. It's wrapping around the solenoid. And now they ask you to find the mutual inductance M. We're going to derive it. Okay, so in this situation here, you can do it both way, but for this situation, I'm going to call this the primary coil. Okay, primary. I'm going to call this circular coil here as a secondary one. Okay, if you look at the situation here, the secondary, they call it a coil, but the primary, they call it a solenoid. So means by this thing here, this secondary coil here, the length is negligible. Means that you don't need to think of it like a solenoid, you think of it as a circular coil, all compressed together on one circle. It's not like a cylindrical shape, it's like a circle. It's a 2D flat coil of wire. Okay, for the secondary coil. For the primary one, it's a solenoid, it has length. But for the secondary, it's wounded on the plane. So you don't need to see any length for the secondary coil. Okay, so the idea is, if I set it as primary and secondary, so there will be current flowing through solenoid. Okay, so this one I call it I1. Okay, let's call this as 1. Let's call this as 2. Okay, then it will cause a magnetic field created by the solenoid. Okay, you have current flowing through the solenoid, therefore you have magnetic field created by the solenoid. So you call this B1. So this magnetic field here will pass through the secondary coil. So let's say you have magnetic field, and the magnetic field will pass through the secondary coil. So you have magnetic flux linkage for coil. Okay, I'm going to call it coil. For the secondary one, I'm going to call it solenoid. Solenoid has length, coil usually don't have length. Okay, so I'm going to call it phi2. Okay, and now I also know that the relationship between them is M is equals to, in this case, this will be phi2, this will be I1, or you can break it open to become N2 phi2 over I1. Okay, this is what we have discussed earlier, but now we are going to break open the magnetic flux for coil 2. We are going to break it open, and we are going to bring in the magnetic field created by the solenoid. Okay, so if you break open the magnetic flux through coil 2, it will become BA cos theta. I haven't labeled the subscript yet. Let's label it together. Okay, the B over here will be the magnetic field that passed through coil 2 over here. But the magnetic field that passed through coil 2 is created by solenoid. primary one, solenoid 1. Okay, you can call it solenoid 1. So this B here, you have to substitute, you have to put subscript 1 because the magnetic field is created by the solenoid. Okay, the area over here, you can see that the area of the solenoid and the area of the coil are similar. Okay, they want to wound it together, but they want to wound it at the same radius. But if they wound it at the same radius, you cannot see the diagram clearly. That's why they wound the second one slightly larger. Okay, but technically they are trying to show a diagram where it's wound at the same radius. Okay, so in this case, the whole secondary coil is going to experience magnetic field. Okay, it's not that because the solenoid is smaller than only the center portion of the actually can. Okay, even if you think I'm going to make this a bit too complicated. Even if the coil is larger, right? Even if the coil is larger, the magnetic field that is passing through the coil will only be this center section only. Okay, you see no magnetic field passing or weak magnetic field passing through this area over here. Okay, therefore the area, no matter what, should be the cross-sectional area of the solenoid. Okay, so over here, I'm going to put in subscript 1 over here instead of the area of the coil. They never give us the area of the coil, but we know that the coil must either be equal to the radius of the solenoid or is larger than the area of the solenoid. So if the coil is having an area larger than the solenoid, then the magnetic field is only happening at the region where it's equal to the cross-sectional area of the solenoid. Okay, I'm making it a bit too complicated. This is a solenoid. Okay. This is your coil. I'm looking at it from the side view. So this is your solenoid. This is your coil. Okay, so because solenoid, there's current flowing through it, then this solenoid here will create a magnetic field inside the solenoid. Okay, but now you are calculating the magnetic flux linkage for the coil, and the coil has such a big area. But when you substitute in the area over here, you are substituting the area of the coil that has magnetic field passing through it. And the area of the coil that has magnetic field passing through is only equal to the area of the solenoid. Because this outside region over here, there will be nearly none, or very weak magnetic field only. Okay, the magnetic field are concentrated inside the solenoid, so therefore you can just take the area of the solenoid to substitute in for your A over here. Okay, it's the area of the coil that is experiencing magnetic field. And the area of the coil that is experiencing the magnetic field is not the whole area, but it's only the portion of the area that is inside the solenoid. That's why you can change it to become the area of the solenoid. Okay, the cos theta over here, well, they are coaxial, so this one you know will be equals to 1. Yeah, they are all sharing the same axis, you know it will be equals to 1. Okay, if you want confirmation, the area vector is also pointing into the page. The B and the A are pointing into the page. The angle is 0, so cos 0 become 1. Okay. So now you end up with N2, B1, A1 over I1. But that's not the end. You know that this B1 over here is the magnetic field created by solenoid. Okay, so this inside here is near the center of the solenoid. Therefore, you can expand the equation to become mu naught N1 I1. Okay, why? Because this is the magnetic field created by the solenoid. And you know that at the solenoid center, B1 is equals to mu naught N I. Okay. They are not putting the coil at the end of the solenoid. They are putting the coil at the center of the solenoid, not the end of the solenoid. If they are putting it at the end of the solenoid, then it's half mu naught Ni, small n. But they are putting it at the center, so it's mu naught small n I. Okay, so know this already. What we can do, we can proceed to cross out things that are overlapping with each other. Then you can expand this to become N1 over L. Okay, so if you expand everything, you see that the answer will be mu naught N1 N2 area divided by length. So this will be the equation for mutual inductance for this setup over here. Okay, for this setup where you have a solenoid and a circular coil around it, the mutual inductance can be determined using mu naught N1 N2 area divided by the length of the solenoid. Okay, so that's it for this question. So I've already derived what you see in the notes just now, this equation over here.